Operators are the most useful and the most widely studied type of linear transform. And an operator is just a linear transform whose domain and codomain are the same. So an operator on V is just a linear transformation from V back to itself. And these are well studied, and so most of the time people just write L of V for L of VV. So the first important thing to know about operators is that for finite dimensional vector spaces, linear operators have the following are equivalent properties. So the following are equivalent TFAE. T is invertible. T is injective. T is surjective. So, invertible always means injective and surjective. So the key point here, the idea behind saying that these are equivalent is that if T is injective, then it's automatically surjective, and vice versa. If it's surjective, then it's automatically injective. So because the dimension of the domain and codomain match, you get something for free. Because it's usually quite possible to have something that's surjective but not injective, or vice versa. And it's definitely true that if your vector space is infinite dimensional, then it's quite possible to have something be injective without being surjective. And there's a couple examples of that in the book. So for the proof, it comes back once again to the rank nullity theorem. And now you're sort of starting to see how many things actually follow from the rank nullity theorem. And so this gives you an idea of why Axler calls it the fundamental theorem of linear algebra. We get a lot of mileage out of it. So the dimension of V is going to be the nullity of T plus the rank of T, right? And we have that the null space of T is trivial if and only if the dimension of V is equal to the dimension of the range of T, or in other words, the rank of T, because the nullity vanishes. Now, if you look at this if and only if here, the left side is equivalent to B. And so by the left side, I mean this one here. On the other hand, since the codomain is V, we have that the range of T is contained in V instead of the W that we usually would be talking about. So the right side, by which I mean this one here, is equivalent to saying that V equals the range of T. And that's equivalent to statement C. And that's enough to prove the theorem. The other parts are trivial.